Hi, this is Merlin, and today the main topic is the x86 architecture. Um, so if you look at here, this part, not this part, oh, no. X86, wait, I can't really find it. Hold on. Open folder, Ubuntu, core repo. Wait, hold on, yeah, here. Um, this is a project that I'm working on. No, I'm not really working on right now, but I'm working on. I did this kind of stuff like 3 months ago. Yeah, it's been 3 months ago, or 2 months ago. So what is this? This is actually um, the obstruction of the x86 architecture hardware level. So what do you mean by that? So I'm a front-end engineer. So when I'm trying to learn about operating system, when I'm trying to make it, there's gonna be learning curve on it. Example, if you're trying to make operating system, you have to choose some kind of low level, C, C plus, C plus or C or Rust or whatever. But I'm literally I'm using TypeScript or JavaScript, and I know the power of using just focusing on one language and go deeply rather than learning a lot of things. So there was learning curve on it, but I didn't wanna like learn those kind of new languages because just for the operating system. So what I did was so even though, so the background is when I try to use assembly in really low level. So assembly is really low level, right? And I learned that even in the assembly, we assume that hardware is already there and hardware is the those kind of things. So there's kind of like mislink or hidden part of the hardware, even though I'm using the assembly. So, and my theory was, if it is, if even though I'm using assembly, I don't know exactly how hardware looks like. So what if I obscure over the hardware specification, like the buffer thing, in using TypeScript, because TypeScript or JavaScript we have some kind of array buffer, create array buffer thing. So that is how I did it. If you look at this CPU part, so there's a BIU and EU. BIU is just like bus interface unit, and EU is execution unit. So it just divided into. Um, and of course, inside BIU, there's a register of it, insert pointer register, whatever stuff. And also, I make the prefetch in input queue. The prefetch queue is just like um, it's just a, it's just the how to say it. Mm, it's just the posting all of the instruction that has to be executed. But yeah, it's just a queue. It's just the queue, but instruction has to be but wait the other instruction do whatever stuff. So that's why I literally made abstraction of it. It's just a queue of it. There's no engineering thing. And the mode of it, so I just declare the constant of it, the mode. So if you're trying to learn about some kind of address mode, like we're address mode. Um, there's gonna be like real mode or protect mode and long mode, and that so in the real mode the bit is 16 bits, and protect mode is bit is 32 bits, and long mode is 64 bits. So I make this as a constant variable, and I try to extend it. And liter endian just basically means that you pour off the necessary um, like the small byte into first, like into bottom, and put the high bytes into on the top. So liter endian just means that. And the x86 is used in liter endian system, so I just made it is liter endian equals 2. And x86 control signals is um, actually, if you look at how does it works, there's an address bus on it, address bus, and data bus and signal. It was control signals, whatever. There's a three types of bus. So bus is basically it's just the highway. It's just a highway, but the car is the address or data or code signals. So address is just the, of course, is going to be address of your memory, and second, the data is going to be data of that's going to be has to be stored in the memory, and third, the control signals. Control signals can divide into a lot of things because based on the processor's specification of it, but normally we we assign like this: read, write, memory, input, and I/O. And read is just a read and write and write. So I just define the control signals because based on the control signals we do some kind of action on it. So CPU buses, of course, I define like this. So if you look at here, we already defined those kind of control signals of it. And if it is mode is real mode, we assign to get the physical address, the the the, the formula is like physical the segment times 16 plus offset. So that's really how it goes. So we get the second or just the base address because we are different of the class, and after that we plus the 16 bits because we are on the real mode, and after that we just get a value from instruction pointer register. And let's see how it goes. Pointer register. Yep, this part. There's no huge difference of it. It's just the register is a register for storing the offset of it. And after that, you have to after you get the physical address, you have to send the data, right? So you put I put so I look at address bus. So address bus is just like it has to be some kind of like wire. It's just a wire. Address bus is wire, but in the obstruction level, there's no wire thing. So what I did was I just defined the address bus into event based in the web API. So like I define as a bus using event, like custom event here. So if there's see if I send it, we create custom event, and if I get it, I do whatever stuff and I dispatch the event of it and sends it, and when memory reads it, so control bus reads receive reads. If the data is false, of course it's gonna be returned, and if it's true, get the address from the address bus. No, there's the read, but the write is just putting here. But normally we just do the let's say the read. When we so there's a control signal bus and the like data bus and address bus, and control signal bus you're just gonna there's a read and a write, those kind of thing, and the memory this is this read if the it just has the signal, it's not event. We have to just okay whatever. So read it is read, let's read it and get the address bus because we have to get the what is the target address, and when you get it you get the get value for the memory using this, and we send it back to it. And of course this get value from the memory is also consists with the formula. There's so many stuff of it. So basically what it does is it's just using the for others decoding those kind of logic. So if you look at here, get just memory value, and we get a decoder list. So and the reason I make it like this because this decoder, the for orders decoding is also abstract class. So I just make even the like for orders decoding because that also has to make truth table. So I already made the truth table in the JavaScript TypeScript level. So the decoder, it just works a real decoder here, and after that you can just use decoder to decode it. It's very simple, and sends back the data to it using data bus. And when the CPU gets the data from the data bus, because we already sent the signal for the control bus, when it receive, we put this instruction because data is going to be instruction, right? And we put the instruction from the prefetch, and we call the enqueue thing. And of course we have to increase the program counter after that. I think it was +1. Nope, not that. Yeah, whatever. But after getting prefetch queue, we get next instructions. And when so EU, so the whole CPU microprocessor get the fetch. So the fetch logic is gonna be like this kind of thing. Of course, that's gonna be fetch logic. After using fetch logic, you decode it. get next instruction is because get next instruction is just the decode of the queue because every the every the ready instruction is going to push into queue, and when you get the instruction you decode it. But I didn't implement it. I wasn't able to implement the decoding because that requires some kind of compiler steps and the table of the opcode those kind of things. So this is it. So this is it. This is it. I have a nice day and see you next time. Bye bye.